Today we're going to be talking about inferential statistics. My name is Jack Jackson, and specifically we're going to be talking about hypothesis testing, about proportions. First, let's recall that in both a hypergeometric and binomial distributions, what we're doing is we're counting the number of successes in a sample of a fixed size. The fixed size of that sample we'll call lowercase n, or n might be the number of trials for Bernoulli trials. And x is the number of successes in that. Now remember, before we go any further, remember that success is just a label that we put on the thing that we're trying to count. It could be a good thing, could be a bad thing, could be a neutral thing. When we talk about the proportion of successes in a sample, we find that by taking the number of successes and dividing by the sample size. So it's the fraction or proportion, or might be at a decimal or a percentage form. But it is the proportion of successes in that sample. And we'll use this symbol p hat, we call it. This p with this little caret above it, p hat. So p hat is x over n, or x is n times p hat. Now the output of the PDF, the probability density function, is exactly the same for proportions as it is for successes, say a binomial or hypergeometric as appropriate. But it just changes the input value to, instead of the input value being x, which it would be for a binomial or hypergeometric, the input value is the p hat for a proportion. So for example, let's look at this example here. Here we have on the left the table for complete table for a PDF and also the CDF for a binomial distribution where n, the sample size is 10, P0, the true proportion in the population, is 0.4, and P hat will be the sample proportion. So on the left we have the binomial distribution. We have the number of successes going down here. It could be anywhere from 0 to 10, whole numbers only. The probability, for example, that x is 3, that exactly 3 successes, is 0.21499. Probability that you have 4 or less, if you add up 0, 1, 2, 3, and 4, these probabilities that go with 0, 1, 2, and 3, and 4, you'll get this 0.6331, etc., and that is the cumulative probability that x is less than or equal to 4. Well, if you just take all these x's and divide by the sample size of 10, and I picked 10 to make it very easy to see the dividing, divide 1 by 10, you get 0.1, divide 2 by 10, you get 2 tenths, or 0.2, and so forth. But notice that the PDF and CDF output values never changed. They stayed exactly the same. Okay? So really, if we want to find the distribution of p hat, we just need to find the distribution of x, and we get the same distribution. So really, when we're talking about proportions or number of successes, it's more or less the same thing. At least it's exactly the same thing in terms of the output. The input is just a little bit different. Now let's recall the difference in a hypergeometric and a binomial on the distribution. So in both cases, x equals the number of successes in the sample. Lowercase n is the number of trials, or the sample size. But the big difference is this. In a hypergeometric distribution, the selection is performed without replacement. So the probability of success is not constant. Let's say you have 10 items, and 7 of them are successes. Well, the first time you have a probability of 7 tenths, or 0.7, for a success. But the next time, your probability of success is either going to be 6/9 if you chose success the first time, or it'll be 7/9 if you chose a failure the first time. So your probability of success depends on what happened in the earlier trials. On a binomial distribution, in contrast, the selection is performed with replacement, or the population size is assumed to be infinite, so the probability of success is the same each time. P0 is the probability of success on the first trial, which is the probability of success on every trial on a binomial, and that is the proportion of successes in the total population. In the hypergeometric, we have a couple other letters that we keep for our parameters. Capital N is the population size, which is some finite number. Capital M is the total original number of successes in the population before you draw anything out of it. So if you divide M by capital N, you get P0, the probability of a success on the first trial. And that is the true proportion of successes in the total population. However, the probability of success on the second or third and fourth trials and so forth is going to be a little different than P0. Here are the formulas that we had derived earlier. And of course, if you really want to go into this a little bit more, you may want to go back to Unit 2 and look at the binomial distribution videos and notes and the hypergeometric videos and notes. But there we derived this formula for binomial distribution. It was n choose x. That n choose x is sometimes called the binomial coefficient or combination. The true proportion or probability of success, P. Back then we just called it P. Here I'm going to call it P sub 0 because we got too many P's around here. But P sub 0 to the x, Q, which is 1 minus P, to the n minus x. The mean of this distribution, or the expected value of x, was n times P. N times P0. And the variance was n times P times Q. And of course the standard deviation would be in the square root of n times P times Q. And in the probability for hypergeometric distribution, the probability of a particular x is capital M choose x times capital N minus M choose lowercase n minus x. And that's all divided by uppercase n divided by uppercase n choose lowercase n. So in the denominator you're dividing by the total number in the population choosing the number in your sample. This is the number of successes in the population, and we're going to choose x of them. This is the number n minus m, capital N minus uppercase m. That's the number of failures in the population, and we're going to choose n minus x of them. So this is how many we're choosing: the successes, choosing the failures, and this is choosing everything in the bottom. So this is basically one of our counting techniques allowed us to come up with that formula. It turns out that the expected value here is again n times P0, where P0 of course is capital M divided by n. So basically the same kind of formula here for the mean, and almost the same formula for standard deviation. Here it is with the original parameters, but if you look at it, this m over n is P0, the original proportion. This is 1 minus the original proportion, so that's Q0. So the variance over here for binomial was NPQ. Here we have NPQ, and then we have this other factor in the front that is capital N minus little n over capital N minus 1. This factor here in the front, this factor right here, is sometimes called the finite correction factor. Okay, so it's basically the fact that we have a finite distribution and we're drawing without replacement turns it into a hypergeometric. And really, the mean basically is kind of the same, but the standard deviation has this extra factor. The variance has this extra factor. Of course, square root of all that would be the standard deviation. So, if we're finding a distribution of proportions, we first find the value of x that goes with that in P instead of just finding the P, and then use a hypergeometric or binomial distribution as appropriate to find the desired probability. Once again, we use a hypergeometric distribution when the selection is performed without replacement, so the probability of success is not constant. And then we use a binomial distribution when the selection is performed either with replacement or the population size is assumed to be infinite, so the probability of success is constant each time. So let's look at some examples. Actually, I have a total of 6 examples that we're going to look at in some detail here. and we're going to go through these one at a time. Okay, our first example here says, suppose there's a set of 40 parts, and it's claimed that the proportion of defective parts is 37.5%. So we take a sample of 10 parts, and we find that one of them is defective. Do we have sufficient evidence to suggest that the true proportion of parts that's defective is less than claimed? And we're going to use an alpha level of 0.1 for this hypothesis test. So, and this is basically like any other hypothesis test, like hypothesis tests we have done for means, for example, in that we have a null hypothesis, we have an alternative hypothesis. The null hypothesis establishes some known distribution, and then from that known distribution we can compute probabilities. The easiest way to do this is with the p-value approach, and that's the approach we're going to be using today. So, see if you can state the null and alternative hypothesis to this. Press pause now. Well, let's take a look at what we have. We have capital N is 40, little n is 10. So that means that we have 40 items in the population. We're sampling 10 of them. The null hypothesis would be that their claim is valid. So P0, the true proportion in the population in decimal form, is 0.375. And so M is 0.375 times 40, which is 15. Of course, M has to be a whole number. It works out to be 15 here. So the null hypothesis is basically that we have a hypergeometric distribution, because when we pull a sample of 10, we're not going to put them back in and sample the same thing more than once. So it's going to be sampling without replacement. That makes it a hypergeometric distribution with the parameters n is 40, capital N is 40, lowercase n is 10, capital M is 15. And that defines a hypergeometric distribution. That's what the null hypothesis says, and that's what we base our test on. The alternative hypothesis is that the true proportion is less than that. So this is a left-tail test. So we're basically trying to find the probability that P0 is less than 0.375 from this distribution up here. Well, a probability of 0.375, as we have seen, corresponds to an M of 15. And so we're going to say, what's the... we're going to test to see that less than 15. So basically we're trying to find the probability that M is less than 15, that the true number of defective parts is really less than 15 out of these 40. So in our sample we only found one defective part. So that was, so P hat is X over N, that's 1 over 10, or 0.1 or 10%. So we only found 10% in our sample. That's certainly less than 37.5%, so it looks like there may be some evidence that the true proportion is less. But what would be a p-value associated with that so that we can make a decision based on data? So to compute a p-value, we need to compute the probability that the proportion from a sample will be 0.1 or lower. It's the same as computing the probability of the number of defectives being 1 or lower, okay, from a hypergeometric with these parameters. So we take our formula for the PDF, M choose K, N minus M choose N minus K over N minus, or N choose little n. And then we add that up for all the ones up to 1. So that's just 0 and 1. So we're going to add that up. This gives us the CDF that goes with 1 for this particular hypergeometric. So this is basically a hypergeometric CDF of 1 with this particular distribution. And that's what the p-value is. Well, plugging in the exact numbers here, we plug in N is 40 and 15. So basically we got 15 for M. So we got 15 choose K here. We're going to choose k successes. K is going to be 0, and then it's going to be 1. Here we do 40 minus 15, which is 25. That's how many successes we have. That's how many failures we have. Remember, in this case, a success is a defective part. Okay, so that means we have 25 good parts, so 25 failures to choose from, and we're going to choose 10 minus k of those, where k is 0 and 1. So when k is 0, we're going to choose 10, all 10 of from the 25, and when k is 1, we're going to choose 9 from the 25. In the denominator, we have 40, choose 10. Notice this does not have any k's in it, so I can factor that out and write the sum only in the top and then divide it by this at the end. So kind of like getting a common denominator, pulling that all out. So we want to plug in k as 0 and 1 and add these up. Now this is only two things, so it's not too hard to go ahead and do these two things separately and then add them up. Go ahead and do that on your calculator right now. Press pause. Okay. Here I have it worked out, and I used a sum formula on the calculator. Okay, and I did the sum of 15 NCR K, close parentheses, times 25 NCR, in parentheses 10 minus K, close parentheses, divide by, parentheses, 40 NCR 10, close parentheses, then comma, K is going from 0 to 1, so K, 0, 1. And we work this out. If you've got the pretty print, or math print I think it's called, turned on, that will look like this. So you write it like you do up here. K going from 0 to 1. Okay, and then you put in your formula here. This is running off the screen, but the rest of this is exactly the same. It just stops here, right here, before you put the K, 0, and 1, which are over here on the sum. And notice what we get for our answer. There's our answer, which looks pretty good there. Over here, I've worked this out actually using Excel to come up with this table over here, and I've got the entire PDF and CDF worked out. So I've gone all the way x from 0 to 8, which are the possibilities. Okay. And actually, it should have run all the way from 0 to, should have run to 10 actually, so that this would sum up to 1. But we got the part we need right here. So 0 to 8, that's the first part of the table. And here I've got the PDF. The PDF I worked out by doing this formula without the sum. So this is the probability that we get 0. This is the probability that we get 1, assuming that there are 15 total in the population. Add those two numbers together, we get this red number right here, which is the same as what we found here. Let me see if I can show you where this sum thing is on the calculator. So pulling up the calculator, at least in the current or the newest operating system, you should be able to find it here. I think it was under list. We can sum a list this way. So if we generate a list, we can sum it that way. So we could go to our table, generate the PDF list, and then sum it up. Say make our list only go down to 0 and 1. We can also do it, I think it's under, maybe it's under math. Let's try this. Math. Yeah. Summation. So you go all the way down to 0 under math, you get summation. And that gives us the command here that you can see here, and then put in the rest of this as it says. Remember, NCR is under math, probability, number 3 there. The rest of it's pretty straightforward. Now, it turns out in Excel, at least the newest version of Excel, there is a hypergeometric PDF and CDF built right in. And so, of course, in Excel, you start a formula with equals. You can actually just type what you see right here in one single cell, and it will come up with this number automatically. Type of formula, you start with equals. It's HYPGEOM for hypergeometric dot dist, D-I-S-T, distribution. And then the order is X, little n, capital M, capital N, and true. And you get this. So in other words, we put in 1, 10, 15, 40, and true, and I get this same number, 0.04 something. True gives you the CDF, false gives you the PDF. So I'd change this to false and left it the same. I would have gotten this 0.03615 number. So if you have Excel available to you, particularly the newest version of Excel, this is very easy to work this out. And of course, if you forget the rule, you can use Excel to help you out pretty easily. Let me show you that in Excel. So here is a hypergeometric. I actually have this distribution set up to where it will, you can actually plug in the numbers. Actually, this is the one we're looking at, 40, 15, and 10. And over here gives you the PDF. Here it is going down to 10. And the CDF hits 1 at 10. And this is 1 minus the CDF, so this is going to, so this basically, the CDF is your left-tailed area, and the 1 minus that will be your right-tailed area. And these are the probabilities of individuals. I also have a calculator set up here, but you can also just type in one particular calculation pretty easily. So the way you can do that, remember, is put this FX button and then go to statistical, and then go down and find the one that looks interesting to you, in this case hypergeometric, and it pulls up a wizard like this. And so you can just type in and it tells you what it is. The number of successes in the sample, 15. The size of the sample, 40. The number of successes, number of successes in the sample was only 1. The size of the sample is 10. The number of successes in the population, that's 15. The population size, that's 40. And you turn true or false. True will be a CDF, and for a PDF, use false. So we want true. And there's the number right there. Hit enter, and it will return that number. So with Excel, it's pretty easy because it's got this built-in function. I used Minitab to draw this graph. Here's a graph of the distribution, and actually the Excel sheet that we were just on also had a graph if we'd scrolled over a little bit. But in this case, I've actually shaded the corresponding tail here. So we're finding the probability of these two numbers, 0 and 1 here. In other words, we're adding up these, adding up the areas of these bars and dividing by the widths. Since the width of this is just 1, which is the same as adding the areas here. So the probability when you get by adding up for that probability of these two bars is your 0.04. So what's our conclusion on this? Well, a p-value was 0.04, and that's less than our alpha value of 0.05. So remember, when p is less than alpha, we reject the null hypothesis in favor of the alternative hypothesis. So this is enough evidence to suggest that the true proportion is less than 37.5. So notice what do we do here. We basically realize that we're drawing from a finite population without replacement. That is a hypergeometric distribution. We use the hypergeometric distribution to compute a probability that we had the hypothesized distribution, which is hypergeometric, then we would only get one or less successes, in this case defective parts, and that probability turned out to be less than alpha, so we reject the null hypothesis. Let's try another example, similar example. Suppose there's a set of 160 parts and it's claimed the proportion of defective parts is 10%. We take the sample of 10 parts and find 3 of them are defective. So first of all, what is the percentage in our sample? 3/10. Remember, success is a defective part. So 3/10 is 30%. That's greater than 10%. So maybe the true proportion is actually greater. Okay? Or is it because we just happen to be sort of, unlucky or whatever, and just happen to get a bad box? Okay? Is this enough that we think that the true proportion is more than that? We're going to use an alpha level of 0.1 this time. So see if you can work through this one. It works very much like the last example. Press pause now. Okay, let's at least start by writing down the null and alternative hypotheses. So capital N is 160. The null hypothesis that their claim is valid, so what's that going to give us? P0 is 0.1, so M is 0.1 times 160, which is 16. So the null hypothesis really is that we're drawing from a set of 160 parts, of which 16 are defective. And we're doing it without replacement. That's a hypergeometric distribution. So the alternative hypothesis is that the true proportion is greater than 0.1. So in other words, M is greater than 16. So since we're looking just on the right side, this is a right-tailed test. See if you can find the probability that goes with that. You can try this with your calculator, but it's easiest if you can use Excel. So if you got Excel, you could pull that up. Well, here's our point estimator for p hat is the proportion in our sample, which is 30%. It's bigger than 10%. Let's go on and see if we can get a p-value for this. So what do we want? We've got capital N is 160. Uppercase M is 16, lowercase n is 10, and x equals 3. And we're doing a probability that x is greater than or equal to 3. Well, that's 1 minus the probability that x is less than 3, but remember this is a discrete distribution. So if it's less than 3, it has to be less than or equal to 2. So it's 1 minus the probability of x less than or equal to 2, so that's 1 minus the CDF of a hypergeometric with these parameters going up to 2. So we want to add up from 0 to 2 this PDF formula, and that gives us, that sum gives us the CDF, and we will subtract that from 1. So here it is with the numbers plugged into it. And of course this is 0, 1, and 2, so we could actually just work this out by hand with our calculator, but one at a time, and then add them up that way, and then subtract from 1. Or we can use the little summation thing on our calculator, or we could use Excel. So here it is with the summation thing on the calculator. On the left here you can see what it looks like in the older operating system or the newer system with the math print turned off. And here's what it looks like with the math print turned on. I've tried to scroll and show you the different pieces of it. And here's the actual table for the PDF, CDF, and 1 minus the CDF. Now remember, what we're really looking at is 1 minus the CDF. So if you look at the area to the right, if you just look at 10, there's nothing to the right of that. And you go and we work our way back as we add it up, and we get this here. Okay. in our Excel, we could just put in equals 1 minus hypergeometric distribution 2, 10, 16, 160, and true, and that would give you the number that we need. So, has a built-in formula for it in Excel, makes it a little bit easier. So in this hypergeometric distribution example, here's a graph of the PDF, and I've shaded the bars. Now actually there are bars going all the way from 3 up to 10, but the bars after these two here are so short that you're not going to be able to see them. But we shade all of these from 3 onto the right would be shaded red, and you add up all their probabilities together and you get 0.064. So it's a right-tailed situation. So let's see, we got 0.064. That's less than 0.1, which is alpha, so p-value is less than alpha. So again, we're going to reject the null hypothesis in favor of the alternative hypothesis. So there is sufficient evidence to suggest that the true proportion of defective parts is greater than 10%. So we're going to conclude that their claim is not right. One more example. Suppose there's a population of 1,200 voters, and it's claimed that the proportion of voters supporting the president for re-election is 60%. We take a sample of 50 voters and we find that 70% of them support the re-election of the president. Now we're going to assume our voters that we sampled are a nice random representative selection. Do we have sufficient evidence to suggest that the true proportion of voters supporting the re-election is different than claimed? And we're going to use an alpha level of 0.1 for this test. What's the null hypothesis? What's the alternative? Well, the null hypothesis, the claim is valid, so we have P0 is 0.6, and so M is 0.6 times 1200, which is 720. And of course we have capital N is 1200 and lowercase n is 50, so we have a hypergeometric distribution with that setup. Now it didn't really say that we were doing the sampling without replacement, but sampling usually is done that way. The alternative hypothesis is just that it's different. So this is a two-tailed test. Now there's a couple of ways to actually go at this, and I'm going to show you, and they give you just slightly different p-values, and I'm going to show you what ways to do this. So we'll start with this way, and for our sample we find the p-hat is 0.7, so x is 35. So in other words, we found 35 voters in our sample out of 50 that were that supported re-election. Okay, now it's a two-tailed test. Now if we assume that this is a symmetric distribution, we'll have p over 2 in each tail. So let's work it, sort of working it with that assumption. Actually, this is probably not the best way to do it, but let's go ahead and it's probably the easiest way. So we're going to start with this. So p-value is twice the probability that x is greater than or equal to 35. And so that means probably that x is less than 35 is 1 minus the probability that x is less than or equal to 34, because there's nothing between 34 and 35 that's appropriate here. And so this is the formula that I put in Excel, and I got 0.1816. So since 0.18 is greater than 0.1, which is alpha, we do not reject the null hypothesis. So there's not a strong enough evidence to refute their claim of 60%. In other words, it's not that unusual. If the true population was 60%, it's not that unusual to get a sample of 50 and get 70% on our sample. Not strong enough to reject their claim. Now really, though, this distribution is not not completely symmetric. Okay, so what we should do, hang on a minute, there's actually a slightly different way we should do this. I'll show you an example a little bit later on of a, not this one, but a different example where we take into account that this distribution is not completely symmetric. Okay, so right now what I want to do is I want to talk about, again, hypergeometric versus binomial. We actually have a hypergeometric situation whenever sampling is done without replacement, and notice that that is a realistic situation. It's very rare that when you do sampling, once you draw somebody's name out to sample them, you put them back in and allow the possibility of resampling them again. And the fact that a finite population is what we have is also pretty realistic. In most situations, there's not really a truly infinite population. But to use this, notice we must actually know the true population size. That's sometimes not as realistic. In a binomial situation, the sampling is done with replacement. Again, that's not so realistic. But if the population is infinite, then the binomial distribution is appropriate. And here is the kind of the key thing. If the population is very large, not infinite, but really, really big, then the binomial turns out to be a good approximation of the hypergeometric, and we do not need to know the population size. So, if the population is really big, drawing out that one item to begin with doesn't change the probability of success very much the next time. So if you have, let's take a small population, if you have 10 items and you have 4 successes in there to choose from, well, drawing one of those is going to dramatically affect the probability of success the second time. If you drew out a success, then the probability of success the second time is no longer 4/10 like it was on the first trial. It's now 3/9, which is quite different probability. Or if you draw out a failure the first time, then the probability of success the second time is going to be 4/9. Again, pretty different than the original proportion, original probability. So if the small sample size, that makes a big difference. But what if you have a million in your sample, or in your population, and you draw out 10? Well, you draw out 1, let's say you have whatever your proportion of successes is. When you remove that one success or one failure out of a million, the probability of success is so close to the same thing that it really doesn't matter. So we'll often use a binomial distribution when the population size is very big. So let's look at some of our 3 examples that we've done so far. And first we're going to look at example 1. And if you remember, in example 1, we had a hypergeometric distribution. We had 40 in our population and 15 successes. We were going to draw out 10 of them. And notice we got a left-tailed p-value of about 0.04. And this is everything's worked out, and actually some other related probabilities are down here. Well, what if we had a binomial distribution that had the same probability of success on the first time, 0.375, and we're drawing 10 from that, and we wanted to find the left-tailed probability for 1, in other words, the cumulative probability that x is less than or equal to 1. Well, this turns out to be 0.06. There's a fairly significant difference there, and in fact, at a 0.05 alpha level, you reach a completely different conclusion. The hypergeometric would say reject the null hypothesis, whereas the binomial would say do not reject. So, particularly on borderline situations, we're going to get we might get a very different result with hypergeometric and binomial if we have a small sample size. Here are the 2 distributions, and if you look at these, you can see the hypergeometric has these bars in the middle higher and the ones on the side a little lower. And so it has a little bit different distribution, actually a little bit less variable. Okay? If I put these 2 on top of each other, you'll see that the hypergeometric in the green is taller here for the middle bars and shorter here on the outside bars. So it does make a difference finding these areas in the left or right tail, for example. Alright, let's get a bigger sample size. Okay, this one we have a population of 160. We only have 16 successes in that total 160, and we're going to draw 3. Well, a right-tailed p-value that we had for this is from example 2 that we did earlier. Turned out to be about 0.064, and if we replace that with a binomial with the same probability of success on the first trial, the same sample size, the same number of successes, and still do a right-tailed test, well, here we got 0.07, much closer, 0.064, 0.070. And so these distributions are quite a bit closer. And if we look at these two distributions, there's still some differences. For example, this bar right here is a little higher than this one, and so forth. But they're they're a little bit closer together in terms of their distribution. So in this case, the binomial would be a better approximation of the hypergeometric. Now this one is a much bigger sample size, 1,200, 720 successes on the first size, and also part of what matters is what percentage of the population we're drawing out. So if you got a really large sample size and you're drawing a fairly small percentage of the population, then hypergeometric is approximated quite well with a binomial. On the other hand, if you've got a sample, a relatively small population, and especially if we're drawing a large percentage of that for our sample, then you'd better use the hypergeometric because the binomial is not going to be a very good approximation then. But in this case, notice we get a pretty good approximation, 0.18 here, 0.19 here. It's a lot closer. And if you look at the distributions, it's a little bit closer for that example. So let's look at an example where we have a binomial distribution that we're going to use. Now suppose it's claimed that 80% of all U.S. citizens support a particular bill. Say Congress is considering some bill. And this one's pretty popular. About 80% of the U.S. citizens support it. At least that's what we think or they claim. And so we want to test this claim. So we do a random sample of 90 citizens and find that 70% of them support the bill. Well, that's less than 80%. Do we have enough evidence to suggest that the true proportion of all citizens that support the bill is less than the 80% they claimed? Let's try to test this with a hypothesis test at 0.05. Now, really, this is truly speaking a hypergeometric distribution because there are a finite number of U.S. citizens. We're doing the sampling without replacement. So technically we have a hypergeometric distribution. But the population size is unknown. So we can't use a hypergeometric distribution even if we wanted to because we don't know the population size. And secondly, even if we did know the population size, we could still probably get by with a binomial distribution because the population is so large that the probability of success each time is nearly the same, even if we don't replace the person we chose previously. So the binomial distribution is practically identical to a hypergeometric distribution in this case because the population size is so huge. Okay, so it's not really going to have any effect on the p-value, or at least not for the first 3, 4, 5, 6 decimal places. They're going to be exactly the same. So it's going to be totally legitimate to use a binomial distribution in this case. So the null hypothesis is the population proportion is 0.8. The alternative hypothesis is the proportion is less than 0.8. Now the observed proportion, p hat, is 0.7. So that means the observed number that we had was 0.7 times 90, which is 63. Now, by the way, when you're doing this, notice that the x value does have to be a whole number. So occasionally you'll see these things reported, and the reported percentage is rounded off. And so if you get a decimal point here, a decimal number after this here, you're going to have to round off x to the appropriate whole number because it has to be a whole number. That's going to be true whether we're using the hypergeometric or the binomial distribution. So the p-value we find is the probability that x is less than 63 less than, I'm going to do less than or equal to 63 actually. Well, here I did less than or equal to 62, so let's go with that. And it's from a binomial distribution with n is 90 and p is 0.8. And here we know how to do this one. It's binomial CDF 90, 0.8, and 62. Okay, let me think about this a minute. I think we're going to include this. So I think really we should change this. Let me change this a little bit because I really think this should be, if this is 63, we should probably say less than or equal to 63. And so let me change what this turns out to be. Okay, so on our calculator we do a binomial CDF, and that's built in, right? So we can go here. So notice that was distribution, and we go down to B, binomial CDF, and the order I believe is N, 90, P, so we're drawing 90 out, P is 0.8, that's the probability of a success each time, at least that's by hypothesis, and we're going to go up to and including the 63. So let's do that. There we go. And this is what we're going to be working with here. Oh. And so that is 0.016 roughly. Again, that is still less than 0.05, so there is enough evidence to suggest that 80% of the citizens support that bill. Okay, so we're going to do these so that the boundary point is included. Here's the distribution here. This one is only going up to 61. Should go up to 63. But you get the idea of the shaded area there. Okay. Let's do another example. In the Journal of Global Business in the spring of 2002, it is reported that 64 of 106 U.S. shoppers reported that the term made in the USA means that 100% of the labor and materials are from the United States. That's how they interpret that statement. Suppose someone claims that 70% of all U.S. shoppers have this same interpretation. Does the reported study produce sufficient evidence to suggest that the true proportion is different than claimed? We're going to use an alpha of 0.05. The population size is extremely large and unknown, so it's appropriate to use a binomial distribution, even though the sampling was likely done without replacement. So the true proportion is 0.7 if the null hypothesis is true. That's their claim. The alternative is that the true proportion is not equal to 0.7, so it's a two-tailed test. In our sample, we observed n equals 106 is our sample, and we observed 64 out of the 106. So that gives us a p-hat of about a little over 60%. So that's less. So that's going to be that we're going to work with that left tail. I think this is the one where I did it two different ways. One way we can do it is twice the probability that x is less than or equal to 64 from a binomial distribution. And here's how we do that. 2 times binomial CDF, 106 in our sample. We're going to, probability of success is 0.7, and we're going to find 64 successes and work that out. So that's 0.04355, etc. So that's about 0.044. That's less than 0.05, which is, I should say, alpha, right here. So that's going to be rejecting the null hypothesis. Since the p-value is 0.044, there is sufficient evidence to say that the true proportion of shoppers with this opinion is different from 70%. Now this assumes that this is a truly symmetric distribution and the left and right tails are the same. If we wanted to do this a more accurate way, what we could do is actually figure out the left and right tails separately and add the probabilities. This is going to give us actually a little bit better p-value. So this is actually a more appropriate way to do it, and I should have done it this way on the two-tailed test in the hypergeometric as well that we did earlier. So notice what we have, the distance from, okay, so what we have, the hypothesized mean is n times p, 0.7 times 106, which is 74.2, about 74. What we found was 64, which is 10, about 10 below the mean. So that means your left tail goes up to 64. Well, where should the right tail go? Well, it should start about 10 above the mean, the same distance above the mean, and then go on up. So it should start at 84 and then go on up to, the top, 106. So notice that our tails should be start about the same distance. And if you look at that, you get just slightly different probabilities for those two tails, because this is almost symmetric, but not perfectly symmetric. So the left tail is 0.0218, and if you double that, you get the p-value we had before. But the right tail is 0.0216, almost the same, but just slightly off. And if you add those two numbers together, you get this number here, 0.034 instead of 0.044 that we got. Wait a minute, that's not right. It should be 0.04, should still round off to 0.044. We'll see what's wrong with this particular screen here. So let's rework this. So we should have distribution. Okay, so for the left tail we should have binomial CDF of 106. We're going to choose 0.7, and we're going to go up to and include 64. That's going to give us the 0.0218. To that we're going to add, parentheses, 1 minus binomial distribution, binomial CDF, 106, 0.7, and how do we go? Okay, I need to go 83 instead of 84 here, because what I'm subtracting is, I want to include the 84 here, so I cannot include it in what I subtract. So this should be up to 83 only. This should be not that. Typo there. Should be 106 here. So I need to insert a 0, and then really should have a closed parentheses there. There we go. So that is going to be what we get when we add these two numbers together. practically the same as the others, so there's really not that much difference because it's so close to being symmetric. So notice here we got 0.0436. Here we got 0.0434. So there's a little bit of difference way over there, but it didn't make that much difference to us because this is almost symmetric. Okay, but if this distribution were skewed more, then this would be we would need to probably take this technique into account. Let's look at another example now. Suppose that a statistics department claims that 95% of the students who do all the assigned homework will pass probability in statistics 1 with a grade C or better. And we want to test this out. So we sampled 20 students at random out of the students who did all the homework, and it's found that 16 of them earned a C or better. Does this data give enough evidence to support the claim the department is overestimating the proportion at the alpha equals 0.05 level? Now 16 out of 20 is 80%. So 0.8 is our p hat. Notice that is less than 95%, so there's a possibility that the department is overestimating, that they're too high. So this is actually a left-tailed test of hypothesis. The sampling is done without replacement, indicating that a hypergeometric distribution. However, the population size is pretty large, so binomial distribution could be appropriate. And it's really the only thing we can do anyway because they didn't tell us the overall population size. Had they done that, we might have used a hypergeometric. The null hypothesis is that the true proportion is 0.95. The alternative hypothesis is that the true proportion is less than 0.95. So our observed data again is p hat is 80% or 0.8. And to find our p-value, we want the probability that p is less than or equal to 16, which was our number of successes we found here, from a binomial distribution when n is 20 and p is 0.95. You should be able to figure that out now pretty easily with your calculator or with Excel. Go ahead and do that now. So we find the binomial CDF of 20.95 and 16 is 0.0159, about 0.016, and that is less than 0.05, so we reject the null hypothesis there. We conclude that the department is overestimating when they said 95%. Now, we've done these 6 examples. 3 of them were hypergeometric. The other 3, while maybe technically hypergeometric, were approximated very well with a binomial distribution. But if the sample size is very large, a hypergeometric and a binomial distribution are very close. If the sample size is also large, both a hypergeometric and a binomial distribution are approximated very well by a normal distribution that has the same mean and standard deviation. And the larger the values are for both for n, np, and nq, the better that approximation becomes. And so here are a couple of rules to show when a binomial or hypergeometric could be approximated fairly well with a normal. If n is greater than 20 and both np and nq are greater than 5, then that's a fairly good approximation. That's one rule I've seen. Another rule that I've seen is if both np and nq are greater than 15. That's a pretty good indication that a binomial or hypergeometric could be approximated reasonably well with a normal approximation. So what I want to do is now take these 6 examples that we've done and see what would have happened if we'd used a normal approximation. So remember here, this is a screen we've already seen today, but here are notice the mean is n times p0 in both cases, and the the variance is npq, so the square root of npq is the standard deviation. Here the variance has this extra factor, n minus capital N minus lowercase n over capital N minus 1, times NPQ. Of course, square root of that for standard deviation. So if it's a hypergeometric and you know the sample size, know the population size, you can use this formula to find, and the square root of that, to find the standard deviation, and this formula to find the mean. Use that in the normal distribution. If you have, if you don't know the population size, or it's big enough that you know it really doesn't matter, you can use a binomial approximation. Just use NP0 for the mean, and the square root of NPQ for the standard deviation, and then use that mean and standard deviation for your normal approximation. Now, let me also talk about a sometimes called a continuity correction, or you're using a continuous distribution to approximate a finite distribution. Here I call it a finite distribution correction. You could rephrase it the other way as a continuity correction. But basically, what would happen is we need to include all the numbers that would round off appropriately. So, in a normal distribution, we want to approximate the probability of x less than 5, what we want less than or equal to 5. We really want to do the normal CDF going up to 5.5, because anything between 4.5 and 5.5 would round off to 5. Okay? So, let's just look at an example here before we get back to our 6 examples we'd seen earlier. So suppose we have a binomial distribution with n is 25 and p is 0.4. That would be an NP of 10, which is our expected value, or our mean, 10. Standard deviation is the square root of NPQ, so that's 25 times 0.4 times 0.6. Square root of all that is about 2.449. So we use that mean and standard deviation and do a normal. So the probability that x is less than 5 from a normal would be a normal CDF going from negative infinity, I just use negative 100 here, up to 5.5, not to 5, but 5.5, with a mean of 10, standard deviation of this 2.449 something. And notice this gives us approximately 0.033. The true probability that x is less than or equal to 5 from a binomial CDF would be n is 25, p is 0.4, and we're going up to and including 5. That's 0.029. So if you round off to 2 decimal places, they're both 0.03. So they're pretty close, although not exactly the same. So here I've have the examples that we've done before. And by the way, let me show you this. This comes from this Excel sheet. I've added a tab recently that goes over here. And the first case, we can just put in, like the other tabs in this sheet, you can change the numbers, the red numbers with the blue backgrounds, you can change. So this one, you can do any hypergeometric, any binomial, and any normal that you want, and it will compute these probabilities. But if we go over here to this second set here, what this is for is we start with the hypergeometric, and this says this would be the binomial that would approximate it, and here's the normal here. This column here, where it just says normal, this goes up to when it says probability, like when it says probability that x equals 35, that's 0 for a normal distribution. And if we go probability less than x or less than or equal to x are the same. But what we want to do really is go up to 35.5 and use those. And we want to do the probability that x equals 35. Then we really want to go between, in the normal distribution, we do from the probability between 34.5 and 35.5. That's that continuity correction or finite distribution correction there. So this is the actual hypergeometric. Here's what we get for comparing it to a binomial. And if we approximate with a normal, this with the same standard deviation that we get from the hypergeometric formula and the same mean, then this is the probability. So for example, well, you can see, there's left-tailed test and right-tailed test and so forth. This set of things on the far right here starts with just a binomial distribution, and then compares it to a normal with the same mean and standard deviation here. So that's what I use to go back here and get this table. So this is back in example 1. What we had was we had a population of size 40. We had 15 successes right here, and our sample size was 10, and we happened to choose one success. We want to do a left-tailed test, so with the probability that x is less than or equal to that. So this number here and this are the same. If we do that with the binomial distribution, we would say the probability of success is 0.375, and we're choosing sample size of 10 is the same, and we choose 1. We use that and find the probability there. We've already compared those two numbers. But now we want to compare this to a normal distribution with the discrete correction, and we get this. And notice actually the normal distribution was actually closer than the binomial in this particular case if we use that standard deviation from the hypergeometric. Here's the actual hypergeometric with the normal with the same mean and standard deviation plotted together. And of course you can see that if you're going to do a left-tailed test, these bars stick out quite a bit, so you're going to get an overestimate. Well, no, you're going to get an underestimate because the area under the normal curve is less than the actual bars. Whereas on the right-tailed test, they'll be exactly opposite of that. Not so good of an approximation here because the sample size is pretty small. This one had a bigger sample size and the approximation is closer, but still not that great. And part of the problem is the probability of success is so small. So because of that, this distribution is skewed somewhat. So here the normal approximation here compared to the binomial and compared to the original hypergeometric. See, notice the normal distribution actually goes into the negatives here, which are not really even possible. Whereas this one starts at 0, has bigger bars here, and then they kind of skewed off to the right. So because of that, this is not such a good distribution, not such a good approximation. Example 3 was another hypergeometric. Now this one was quite large sample, 1200. The probability of success is closer to a half, so it's very close to being symmetric. And if you notice, this is actually a pretty good approximation here. 0.182 for the hypergeometric is the actual. The normal is 0.185. Pretty close. 0.191 for the binomial. And here is the normal plot on top of the true hypergeometric. Pretty close. So this would be one where a normal distribution would be pretty decent approximation. Here's a binomial, 0.8 and then 90 for the sample size. And here we get a left-tailed test. Both are very small p-values. But this one is a bit bigger. Again, not a bad fit there though. Pretty close. Example 5. These are pretty close. 0.0085 or 86. 0.0082. Those are quite close. Your graphs are going to look pretty close to each other. And example 6. Now we get a skewed thing here. The sample size is small. Not such a good approximation here necessarily. Now here's the thing. Most textbooks exclusively use a normal distribution approximation for something that's truly binomial or hypergeometric when they're performing inferences about proportions. Now, that's actually problematic because the real p-values should come from a normal, instead of a normal distribution, they should be coming from a binomial or hypergeometric distribution. In fact, most of the time, really from a hypergeometric. However, this normal distribution does give a pretty good approximation. In our case, it's really just about as easy to find these probabilities from especially from a binomial, because we have a nice binomial CDF built into our calculators, just like we have a good normal CDF built in. The only problem is we don't have a good inverse binomial built in, and we do have a good inverse normal built in. When we get to Excel, we have a very nice, not only can we use a binomial CDF, which is built in, as well as a normal CDF, we also have a hypergeometric CDF built in. So if you've got Excel, there's no reason at all why you shouldn't be able to just go ahead and use the hypergeometric or binomial CDF as appropriate and have no problems with it at all, especially in terms of finding p-values. However, since the textbooks do it this way, for example, your textbook just uses a normal approximation all the time, it just sort of checks to see if it's reasonable before it goes, then the homework problems will be done using the normal distribution approximation. So if a homework problem causes you to do a hypothesis test or any kind of inference for a proportion, unless it specifically says something about a binomial or hypergeometric distribution being used, you're going to use the normal approximation. So most of the homework, since it's generated by the textbook authors, most of that homework is going to be done with the normal approximation. And we're going to give you another video on using some further shortcuts with the calculator in using this normal approximation to a binomial distribution or hypergeometric. Okay, however, you will need the techniques from this video if you're ever testing proportions when the sample size is fairly small. Okay, you're going to need to be able to apply the techniques for this. And there may be a few homework problems that ask you to do this. Okay. And that concludes our introduction to hypothesis testing on proportions.